be sharing with you what a one-to-one correspondence is. This is also known as a bijection. Well, actually, I'm going to be sharing with you what my view of a one-to-one correspondence is. And one of the ways that I like to think about this is that one-to-one correspondences are used to count things. They're used to count things. So I guess I don't need to raise that up yet. So the example that I like to talk about is how we first learned how to count things. And so pretend these things are things that I'm drawing. They're chocolate chip cookies. And here's a hand. Oh my, it looks kind of scary. Um, but when I learned how to count, and I know that probably a lot of people learn how to count, they use their fingers to match up with the objects that they're trying to count. So in this example, I have uh, one cookie here, so I'll start with one of the cookies, and I'll raise a finger. And in doing so, I'm going to match it with this cookie. Uh, Now I have another cookie, and so I raise my second finger. And in doing so, I match it or I pair it with the second cookie. And in doing so, I count one, two, and so I know that I have two cookies. And how do I know this? Because one, I paired each cookie with a finger, and I'll say it's a raised finger, uh, and then the second thing that I did, um, well, I wanted to write and there, but I'm running out of space. Uh, so let me just erase this here. Okay, much better. So the first thing I did was I paired each cookie with a raised finger. And the second thing is I paired one and only one raised finger with a cookie. So um, now let's go back and talk about what this one-to-one correspondence is. Well, a one-to-one correspondence is it's a function, but we're not really going to get into that part. But it has two special properties. It's both one-to-one and it's onto. And what this means is that, um, well, I don't know if I want to get into the real technical explanations of what these are, but you can see that it's one to, this example is one-to-one because, well, like I said down here, I paired one and only one raised finger with a cookie. Therefore, if my domain is the raised fingers, so here's my domain, they're the raised fingers, and my codomain is the cookies. I have for each element in my domain, which are the raised fingers, there exists one and only one cookie that is paired with in this way. Therefore, I know that this matching is one to one. Uh, Now, I know that this matching here is onto. Why? Because every cookie, or for each cookie in this codomain of all the cookies that I'm counting, there exists a raised finger which is paired with it. So I know that this is onto, and therefore, uh, when I count in this manner, I say that there are two raised fingers. Oops. Oh no, don't need that. Don't need that. There are two raised fingers, uh, and I because of that, I know that there must be two cookies. because the number of elements in the set of Ray's fingers is the same as the number of elements in the set of cookies because I matched them with a correspondence that's both one-to-one and onto. Now, uh, you might be thinking, well, this is pretty technical for counting cookies, and you're right. Um, but when we have sets of integers and rational numbers, these are infinite sets. And what the set of integers contains the number 0, and also 1 and -1, 1 and -2. And this set also contains the numbers 0, 1 and -1, 1 and -2. But it also contains stuff like positive and -1/2. So there are elements in this set that are not in this set here. 1/2 is not an integer. But we know that, so one of the ideas that you might think of is if you're to count the elements, that the rational numbers, you might say the rational numbers Q has more elements than the set of integers. But this would be a mistake. That's wrong because we don't think about counting like that. We will go back to what we did here. If we can pair each rational with each integer with if there's a one-to-one correspondence between the integers and the rationals, well then in this case, following this idea, we'll say that they have the same number of elements, and that's what we actually find. There is a way to pair this off, and so we know that Q has the same number of elements as the integers, even though Q contains elements that Z does not. And the reason why this is that we're able to, that this, well, I was going to say makes sense, but I think it's better to say the reason we're able to say that is because Q, here we go, that the set of natural numbers, the set of integers and the set of rationals, they're infinite sets. So they do some, they have somewhat of a non-intuitive behaviors in this case. And so that's why when mathematicians were viewing this, they were looking at these sets and they were saying, hey, this is kind of weird. They went back to the very basics and they said, okay, how do we actually count? We'll give names to these pairings, and we'll give names to these operations like, well, not operations, but these ideas of one-to-one and onto, and they gave names to the finite things that we do, and in doing so, we are able to understand something that's much more difficult to comprehend, infinite sets. And so that's what the idea of a one-to-one correspondence is. They're used to count things, and we build from what is familiar with us, finite sets, or counting in finite sets. Counting in finite sets. And we use that to understand counting in infinite sets. Okay, and that's one of the ways that I view one-to-one correspondences.